a PhD candidate from Washington State University, and my advisor is Dr. Zhipeng Li. Today it's my honor to be here to introduce our recent research work. The topic of this presentation will mainly focus on the laboratory investigation into improving the physical resistance of geopolymer, flash-based geopolymer. Here is the outline. First, I'd like to introduce some background that why do we need to develop this geopolymer. And the second part is I will introduce the sample mixture. Then after processing the physical procedures, we tested some micro performance, and then we conduct the microscopic analysis. For the final part is the summary and the future work. As it's well known that Poland cement is widely used for infrastructure, for example, the construction of building, bridge, and pavement. However, recent years, its environment concerns has been widely reported. And the first concern is the huge CO2 emission, and it's reported that the CO2 emission from cement industry is about 5% of the global CO2 emission. The second concern is the huge energy consumption. We can learn from the right figures. The green line is the global cement production, and the orange line is the global energy consumption. So it's very clear that there is a positive correlation between these two. And so for achieving sustainable infrastructure, we need to find something more green and environment friendly to replace traditional Portland cement. Here, geopolymer is a promising candidate. Usually, geopolymer is made from some solid waste, for example, the fly ash, slags, and the red mud. Or those raw materials is cheap, so geopolymer composite is more affordable than cement. In addition, there is no CO2 emissions, and there is no huge energy requirement. So geopolymer is more environment friendly and sustainable than cement composite. However, the development of strength of geopolymer is much slower than the cement. So the lower strength and some weak durability of geopolymer usually hinder its development. And to address these two concerns, we introduce graphite oxide. Graphite oxide is a two-dimensional nanoset, and that's fixed on many functional groups, which can be detected by FTIR. So all these functional groups played important and special roles in the hydration process, and I will introduce in later slides. And the left table provides some physical properties and the chemical composition of Portland cement and Class C fly ash. So based on the difference of the chemical composition, we did some adjustment and introduced some chemical activators and to prepare geopolymer. We employed the uniform design. We employed the uniform design and prepare 36 samples. Then we test the strength and collect data, do regression analysis and optimize the regression model. Then we can obtain this target sample, which features the highest strength performance. The proportion is listed here. Based on our previous research, which at least on the bottom of this slide, we fixed the mass ratio of GO to flash of 0.02%. And we tested the compressive strength of this two geopolymer sample, but however, the result is not as desirable as we proposed. So we want to improve the physical resistance, and to simulate the real winter road maintenance operation. So here we try to improve the salt scaling resistance. Here we propose 3 strategies. The first one is to add mixed air entraining agents, which will introduce lots of tiny bubbles and then improve the freeze-thaw resistance. The second strategy is to add mixed mask of fibers. And here we propose to use this fiber to increase the integration of microfiber after salt scaling. And the third one is to add mixed polymeric agents. And this strategy is based on our previous publication. Or these 3 polymeric agents will slow down the water absorption and increase the water contract angle. And that means to make the samples start haze water and keep it out. Based on these 3 strategies, we fabricate 3 geopolymer concrete. The first one is the concrete contains only air entraining agent. The second one contains both graphene oxide and air entraining agent. The third one and the fourth one contains fibers and polymeric agents, respectively. And before the salt scanning, we test the strength and the water absorption of these 4 concrete samples. From these figures, we can see after adding graphene oxide, the strength of concrete increased from 53 to 63. But after adding fibers and the polymeric agent, the strength was decreased a little bit, especially for the fiber one. But this is a common issue in fiber reinforced composite. We also test water absorption, and we find adding graphene oxide, the water absorption decreased, and then after adding polymeric agents, the water absorption continues to decrease. And based on this result, we briefly summarize that geo benefits the property of geopolymer concrete, and the polymeric agents benefit the water absorption of geopolymer concrete, but the fiber seems showed negative influence. And the positive influence induced by graphene oxide, we have test and summarize many mechanisms in our publication, and the main reason is that geopolymer makes the microstructure more denser and then increase the water contract angle to keep the water out. Here we test the strength after certain salt scaling cycles, and we find the sample 2, 3, and 4 are better than the original sample. And the more specific, we can say sample 3, the green dots. In the beginning, the strength is a little bit lower than sample 2 and sample 4, but in the later age, the strength is a little bit higher. This result indicates that fiber did have some benefits on increase the freeze-thaw or salt scaling resistance. And so here we briefly summarize that, or these 3 samples, the better performance of these 3 samples can be attributed to the increased strength, decreased water absorption, and increased structural integration, which was for sample 3. So how does geo affect the hydration of geopolymer? Here, we run the SEM analysis, and we find
you have 4 minutes left, Zhipeng.
Okay, thank you. And we found that geo reduced some fantastic layer-by-layer hydrates. So this means the hydration is more integral, and we didn't detect obvious cracks on this SEM. Here we run the XRD and the DTG analysis. So from the XRD results, we detect some potent diet, the CH, in the control sample. The control sample means the duopolymer without duo. And we also find that CH disappeared in the target sample. This result was also confirmed by the DTG results. So combine these two results, we can summarize that graph oxide accelerates the hydration process. That means the hydration in target sample is much faster than that one in control sample. And that means more potent diet is assumed, was consumed. Based on when we run SEM results, we also do the EDS analysis. Here we mainly focus on some K elements, for example, the calcium and the alumina. We can say that after adding graph oxide, the relative concentration of calcium was increased, but the relative concentration of alumina was decreased. Based on the relative concentration, we calculated the Moore ratio of calcium to silica and calcium to silica plus alumina. And we find that both these two Moore ratio was increased after adding graph oxide. Based on the model on the top of this slice, the M is the alkaline element. So in this study, it should be the calcium. So the increased Moore ratio means that Z was increased, the coefficient of M. The meaning of Z is the degree of polymerization. That means so at here we can summarize an important conclusion that graph oxide increased the degree of polymerization of the hydrates. And here we also do the EDS before and after phase salt procedure. I just mentioned this was only phase salt in pure water, no sodium chloride. We can find that the leaching of calcium was slowed down by the presence of graph oxide, and then the calcium to silica Moore ratio was also decreased slowly. And here as I mentioned in the beginning, the functional groups makes the graph oxide negatively charged. So this negatively charged graph oxide will attract the calcium but repel the alumina oxygen tetrahedron. And this result also agree with many other publications.
You have 1 minute left, Zhipeng.
Okay. Here is the NMR analysis. So based on the location of the silica oxygen tetrahedron, the basic unit can be classified into 5 groups. From this NMR analysis, so after adding graph oxide, the Q1 decrease and the Q4 increase. This means the hydration product was converted from simple formation to some more complex formation. Here is the summary. First, nano-modified geopolymer shows a promising potential to replace pollen stamen. And graph oxide microfibers and polymeric agents can be used to improve the freeze-thaw and the first scanning resistance. And graph oxide plays many important roles in the hydration process, and then enhance the property of geopolymer. The future work will focus on more fundamental research, including the dynamic modulus, the change of hydrates in the salt solutions, and the leaching behavior. especially for some heavy metals. Any questions?
Zhipeng, could you go back to that acknowledgement page? That was like very short. I didn't really see it. All right. Yeah, probably one thing to add is we do have a patent granted, international patent granted on this technology.
Yes.
All right. I think people could follow up with you if they have questions, because we need to move on to the next session.